transparent to this light. If it's not transparent, it would absorb all the light, and you will see anything. That's the third parameter, which is very important when you talk about scintillators. And the decay time, that's the time, then the scintillator decays and produces light. Should be as fast as possible in order to have pretty fast detectors and process signals immediately. One more thing is that not all materials can be very big. In some applications, you have to exploit big detectors, and these materials, these technologies of scintillators should be able to scale them and create from small detector to a big one. And the last thing that is very important, that the refraction index of scintillators should be equal or is very close to the refraction index of the glass, because we have to couple our scintillator to a photosensor, which frequently has an entrance window, which is made of glass or material with the index, refraction index, which is close to this 1.5 value. So, as I said, this picture exactly shows the thing which I said in the third parameter, which is called the medium should be transparent to its light, because when you have a scintillator, it emits light at an exact, it has a spectrum of its light emitted. Yeah, you can see it emits a light at different waveforms, and they're governed by this spectrum. And this is emission spectrum. And if you have a material which can absorb this light, you will lose of this light, and you can work here this intersection. So that is why it's important to have materials that absorption is much less for this emitting light. As I said, there are two categories of organic of scintillators. There are organic and inorganic scintillators, and here you can see some basic differences. Inorganic mostly are crystalline materials, like, for example, sodium iodide, I will discuss later. And organic materials can be also solid materials, like plastics, for example, or liquid materials, like solvents, and it can be in both states. It doesn't matter. But the main difference, there is no this crystalline structure. And due to the chemical differences between two types of materials, they have such things like different Z number, which is low, always low for all organic materials which contain basically carbon and hydrogen. These materials low, and of course low density for all organic scintillators. The density is approximately equal to 1 gram per cubic centimeter. It can be a little bit less or a little bit more, but on average, it's about 1 gram per cubic centimeter. On the opposite side, you have inorganic materials with high Z elements, that also can have much more dense structure, density up to 8 or 9 grams per cubic centimeter. Some materials can be doped and undoped. I will tell you the difference. And of course, one of the most important parameters: how many photons do you get from 1 MeV of energy of an ionizing particle? That is parameter called as the light yield, and for inorganic materials, it's basically in 4 or 5 times higher compared to organic materials. It depends on the specific level. There are inorganic structures also which have low light yield, but if we talk about conventional materials, this figure is basically high compared to organic materials. And one more parameter, that's the decay time, how quickly your excited state decays. And here I would like to come back to the last lecture where I was talking about exponential law. Yeah, you have, for example, a nuclide that decays exponentially, and you have lower number of radionuclides. Yeah, they decay with time. The same thing happens here in scintillators. You have a lot of excited states, a great number of excited states, and then with time they decay, also exponentially. That's the same law as I said. This law is applicable to many applications, and the same thing with the decay time. It's the thing that you should understand, that you have not one atom or molecule, you have an ensemble, great number of these atoms which decay with time. And here we can derive from this exponential decay the decay time, which is measured basically in nanoseconds to microseconds for inorganic scintillators, but for organic scintillators, this time is usually in nanoseconds region. Organic scintillators are more fast compared to inorganic. That's why they're used in some application where the time is a crucial factor. And the cost, yeah, this is a crystalline structure, and it requires some specific techniques to produce crystalline structures. For example, you have to grow the crystal, for example, by Czochralski method. It's quite expensive. It requires some technique, and organic scintillators are simple in production. That is why they are much more, they are less expensive. Oh, sorry. Stop. Okay, let's talk a little bit about the structure of inorganic scintillators, because inorganic scintillators have structure with the which is called crystal structure. You have that's a common thing for all solid materials. You have a conduction band, you have a valence band, and you have a band gap between these two zones. But I will give more details about this structure in my next slides, which cover solid state detectors. Here, just I would like to say that you have a crystal, and in this crystal, some crystals can pure, but for some purposes, we usually add some extra materials to these crystals, which are called activators. And these activators, they're impurities, which create special site in the lattice, where specifically at the band gap structure, and by this, the energy structure is significantly modified. And this allows to create the light when the electron comes from the valence zone to the conduction zone, when it gets some energy from the ionizing particle, and this energy lies in the visible range. Yes, simple explanation. So basically, materials have a trace amount of these activators. Some inorganic scintillators can be pure crystals. Some always require these activators, specifically sodium iodide crystal that requires thallium dopant in order to improve its ionization yield and make it a scintillator. So here's the process, how it happens. You have the lattice, you have created an electron which can move from the valence band to the conduction band. There is a hole created also, and when they, in simple words, meet, they create a neutral state, which is actually located in the excited state. And then this thing happens. This excited state goes to the ground state, and it emits light. And specifically, this light, the wavelength of this light, light strongly depends on the activator, where it is located. And for these purposes, usually materials like alkali halides, you can see very popular scintillators, sodium iodide, which is doped with thallium, cesium iodide, that's the second by popularity used scintillator, also doped by thallium, also it can be doped with sodium as well, lithium iodide, and so on. This is some examples of activated scintillators, and there are some examples of slow inorganic crystallites, for example, cadmium or BGO crystals. More techniques were developed in order to increase the speed of these processes, because sodium iodide is a good scintillator. Specifically, it can be used in many applications. There are some problems with this crystal, but in general, it works well, but it's not very fast. And about 30 years ago, on the market appeared new types of scintillators. You can see here the majority of them, basically, they are serum activated fast inorganics like LSO, for example, or lanthanum brom 3. That's one of the most popular and important scintillators in the modern gamma spectroscopy, for example. Also, I would like to add that we consider, in addition to crystalline detectors, also noble elements and noble gases. Also, we consider them inorganic scintillators because, as I said in my last lecture, in noble gases, in gas field detectors, you can create electrons, ion pair, electron-ion pairs, can drift, and create an electric signal. In noble gases, there is also a process which leads to, in addition to creation of ionization electrons, you can also get excited states. And the main difference that compared to other materials, that noble gases actually, this is a monoatomic gas, yes, and in order to create scintillation light, it should interact with here a simple picture how it happens. We have an ionization and excitation of one atom, for example. But this atom cannot emit light. It starts emitting light only when it meets the second atom. It forms the so-called dimer state, and then it de-excitates through the dissociation and creates ultraviolet light. The same things happens when you have a positively charged ion. It meets the second atom, creates a positively charged dimer state, ionized molecule, and then it meets an electron and creates also an excited state. And these things goes here and also creates ultraviolet light. Just want to tell you that that's the main problem actually with noble gases in order to use them as scintillators, because they emit light in ultraviolet region less than 200 nanometers. And in order to detect this light, you have to develop specific photosensors, because the majority of photosensors are sensitive to blue light. This is a list. I just actually took this list from one of the main manufacturers of these scintillators. That's a global company called Saint-Gobain Crystals. And this is just a table. I don't know, is it clear? Because there are some unclear figures, but I can just pass through this table, show what usually when we choose some scintillator or to solve some task, we have to understand the parameters of this scintillator. And for example, let's start with one of the most popular scintillators, which is sodium iodide. Here you can see this material. Here, if it's unreadable, I can read you the name of tables. The first one parameter which we look at, this is light yield. This is actually the number of photons per emitted energy. It can be in number of photons per keV or per MeV. Here it's in keV, and we have about 30 photons per keV. Also, the second thing that we look at is decay time. Usually it's for sodium iodide 250 nanoseconds. And the third parameter, which is very important, it's the wavelength of maximum emission of light. As you remember, I said that you don't have one single light. You have always a spectrum of light which is emitted when the excitation happens. And you have to look at the maximum of this spectrum here it's about 400 nanometers, which is actually blue light. And as you can see, this column, almost all scintillators have light in the blue light region. It's about 400 nanometers, and some scintillators have the light at 500 nanometers, also, which is the green light. But there are not so many of scintillators. But this light can, this green light also can be detected as well. Refractive index and density. Here you can look at density. If the material is more dense, you can more easily stop the gamma radiation, all kinds of radiation. That's the main thing. And the same things for scintillating materials as well. Here are some figures 5. And one of the most dense materials you find here, for example, VGO, with the density of 7 grams per cubic centimeter. And the parameter, which is it's not very important, but some applications you should think about it. It's called hygroscopic property of a scintillator. It means how it absorbs light, water or not. Some materials, if they absorb water, they lose their scintillation properties. And that is why it's very important to keep them encapsulated, fully isolate from vapor, all surrounding conditions, and keep it carefully. But that's one of the main disadvantages, for example, of sodium iodide crystal, which is white hygroscopic. It's actually they put that. Yes, and here are some applications how these scintillators are used. I can skip it for now, and because I'm going to explain some of its applications in my lectures. Here we can start talking about organic scintillators. Just start from here. Here, usually we have a 3-component structure of all organic scintillators. Basically, this is a solvent, and we add that's about 98% of all material. We add about 2% of scintillator and add a little amount of so-called secondary fluor that serves as a wave length shifter. I will explain what it means. And I'm not going to deep into a lot of details, but just to stress that the main difference in the fluorescence mechanism of organic scintillators, that's actually you don't have a crystalline structure, and you have only an ensemble of excited molecules. And these molecules get some energy from got the energy from the ionization radiation, and when it goes to the ground state, it emits some amount of light. And here you can see some so-called multiplet structure of the molecule. You have singlet states and triplet states, and the light is the intensity of light is explained by this question, which I also touched a little bit in my previous slides. And here I just like to show you that sometimes in materials there can be not one decay time constant, but even 2 or 3 decay time constant, because we have more complicated structure on the molecular level. We have singlet and triplet states, and the process of going from the singlet states to the ground state is much quicker compared to the time which requires the light to come from the triplet states to the ground state. And that is why sometimes we have quick fluorescence, phosphorescence, fluorescence light, and a delayed phosphorescence light. We have also crystals. For example, one of the most important materials is anthracene stilbene, but the mechanism is the same. They are not pure crystal materials which require this transition from the conduction to the from the valence to the conduction band. And liquid organic solutions, basically solvent plus imperator plus a wavelength shifter, because sometimes it's necessary the maximum of light which is emitted can lie in, for example, in the green light region, and we want to a little bit change the wavelength of this light. You add one more component and get, for example, blue light, and this allows us to improve our detection capability. Plastic scintillator is basically just dissolving and polymerizing materials. That's why by doing this we can have solid structures. And let's move to the one thing that allows us to detect this light. We have an interaction which happened. We have a lot of excited states which leads to a flash of light. And now we want to detect this flash of light with a photodetector. And actually, now there are two types of photodetectors which I'd like to discuss. The first one is a photomultiplier tube. This is quite well-known device. Actually, it was invented in Russia in 1930s by the Russian physicist Ph.D. And now, despite that this device was developed almost 100 years ago, it remains useful and remains a conventional photodetector which is used in scintillators. And this device is pretty simple, and there are two mechanisms which allows you to detect light. And the main goal of this device, is to convert your photon into electric signal. That's the first purpose of this photomultiplier tube, and the second one is to amplify your signal. And how it works: you have a tube. It's vacuum sealed. There is vacuum inside, and you have a photon, which this is a light photon which was created in a scintillation detector. You have, of course, a lot of them, but let's move to the simplest way: just one photon, and you have a glass window. Remember, I told you that you have a diffraction index which is close to glass because you have glass window in the photomultiplier tube. And the second structure, which is located inside this vacuum tube, this is a photocathode. And for the cathode, that's quite a thin structure, which allows you, due to the effect which I covered in my first lecture, which is called photo effect, to create an electron instead of photon. And how it happens, you have this structure, this is optical window, this glass window, and you have about 30 nanometers thick photocathode. That's very thick for very thin material, because if you do it to make it too thick, it would be impossible for an electron to escape from the photocathode and go into this room, into this space. And what happens? That's simple photoelectric process, which I think you know. Photon is converted into electron. And this electron starts moving inside this vacuum tube. But in order to make it moving, you have to apply an electric field. To do this, we have this structure of these metallic pretty thin plates, which are located inside this vacuum tube, which are called diodes. They are made of metal as well. And the main thing of this, the main goal of these diodes is to amplify the signal and create more and more electrons. Here is the first process, photoelectric effect or photoemission, and the secondary process is called secondary electron emission. And what happens here? Electron is moving inside this vacuum tube and hits the diode. And as a result of this interaction, this electron gives rise to more electrons. There are more electrons emitted from this diode structure. For example, for one electron, initial electron, you will have two electrons, and these electrons also interact with this diode, strike it, and create more and more electrons. And actually, you have some sort of an avalanche compared to the thing I mentioned about gas field detectors, but that's a little bit different because you have a vacuum here, and all electrons are produced through the interaction with this diode structure. And this process allows you to significantly increase the number of electrons. For example, one initial electron, at the end of this way, you will get up to 1 million electrons. So when this electrons comes to the last diode or the anode, you can collect them and get the electric charge. And this charge can be processed like in ionization chamber. You have a capacitor, a resistor, they will get an amplitude in voltages, and the amplitude, the value of this amplitude is pretty high compared to some other types of detectors, and you can use, for example, a simple preamp and feed it to your data processing system. The main disadvantage of this photomultiplier tube that in order to create this amplification, you have to apply pretty high electric fields, up to 1.5 kilowatts of voltage in order to create about 100 volts of electron volts between all diodes, because if you get less, you will not get enough energy to create these additional electrons. And one of the most important parameters of the photomultiplier tube is called the quantum efficiency, because not all initial photons go to electrons, because there is also a probability. And on average, this number is from 20 to 30% quantum efficiency. Here you can see how this device looks like. Different geometries, different sizes. You have small devices with a diameter of about half of inch, about 1 centimeter, and two large EMTs with diameters for about 20 inches, half of meter. It depends on the size of the detector or the application of the device. Here that this delta number tells you the number of secondary electrons emitted per primary incident electron, and if you multiply the number of these diodes and the probability to create the secondary electron, you will actually get their amplification factor, which is called a gain. And this number, as I said, can be up to 1 million, even more. But basically, it's something 5 times 10 to the power of 6. That's the gain. PMT quantum efficiency strongly depends on the light, because if you have the wavelength, the photoeffect process differs for different wavelength of a photon. For example, for ultraviolet photons, you have more energetic. Yeah, if the wavelength is shorter, you have more energy for your photon. That is why this quantum efficiency depends on the wavelength of your photon. And operating voltage, as I said, usually from 1,000 volts to 2,000 volts. Sometimes it's not important, but there are some also parameters, but I'm not going to deep into details. Should be time resolution, how quickly you collect your light, how transit time, how quickly electron avalanche moves inside this vacuum tube, linearity, because you have uniform response to low flashes applied and to big flashes applied. You have to understand that your response is linear in a big energy region. And there are some spurious effect like dark noise, which is mostly caused by fermionic emission of electrons from the photocathode. And now that was a vacuum device which was invented almost 100 years ago. And during the development of semiconductor materials, physicists started to consider new opportunities to detect light, and came up with an idea to use silicon, which is used in basic materials, semiconductors, transistor diodes, and so on. And they came proposed to use these silicon diodes in order to detect light. And the main difference here that you have not so-called external photo effect, which actually happens in this photomultiplier tubes, because your electron from the surface of the photocathode goes to the vacuum. Here is called internal photo effect. When you your photon actually can create an electron inside these semiconductor materials. And this electron can, if you have a flash of light, this light gives rise to electrons. If you have pretty intense flash of light, you have a lot of electrons, and it leads to electric current in simple groups. And this is a device called a photodiode. That's some sort of semiconductor replacement to the photomultiplier tube, but it can't fully replace it for several reasons. And the first reason that in this semiconductor material you can't detect people lights, single photons. The main reason you don't have an amplification of this structure. You have the same thing. You have to apply it in electric fields, of course, in order to collect your electric charge. Yes, and this field is not high enough to amplify the signal, and you don't have gain. And if you don't have gain, you can't detect single photons. And physicists started to develop devices which can do this thing, and they proposed to apply high electric field to the photodiode and invented the second type of the photodiode, which is called avalanche photodiode, because they applied high electric fields to this semiconductor structure. And here you can see the picture. You have an initial photon which creates electrons, and these electrons start moving under the influence of electric field. And if you apply high electric field, like in gas detectors, you can create an avalanche. Your electron has enough energy, it gets from the field, from the external field, and it ionizes the matter. And doing this, you can create avalanches of electrons and significantly improve your amplification. But it wasn't enough. The maximum gain that can be achieved with this type of detectors, you can see them. This is how it looks. It's just about 5 millimeters or 10 millimeters in diameter. It's pretty small device, and the main gain you can get is about 100, because you have one problem that applying high and high voltage, you are starting to get discharges, and you can produce this uniform structure. And this led to the problem that physicists starts to think about creating the actual device that can replace the photomultiplier tube, and came up with an idea which is called a silicon photomultiplier tube, and actually not tube, simply silicon photomultiplier. There are lots of names for this device, but originally, I'm proud to say that this device was the idea. Silicon photomultiplier was belongs to Russian physicists, and they in 1980s constructed this device. What is their structure, and what is the advantage, and how they keep this thing that they can apply higher voltages to this semiconductor structure? They decided to apply much higher voltage, much higher. And this voltage, like in gas field detector, it becomes Geiger mode regime, Geiger mode area. But as you remember from my previous lecture, that when you operate a detector in a Geiger mode, you lose all information about the energy. The number of created electrons is not proportional to the number of initial electrons. Here, number of initial electrons is proportional to the number of photons, and you lose this dependence. And in order to get rid of this problem, physicists created a matrix of small semiconductor structures, which are called pixels, like in our smartphones, where have CCTV detectors to detect light. They have a lot of pixels. The same thing with silicon photomultipliers. They have about modern detectors have about 20,000 these pixels, and these pixels, they are structured on the same substrate, and the reason they decided to create a lot of pixels, because all pixel actually is an independent, and if you have, and they're pretty small, about 25, 35 micrometers, and when a photon hits a pixel, it creates, as in the conventional photodiodes, actually, this is an ensemble and a matrix of avalanche photodiodes. You have a lot of small photodiodes which are located and connected to each other. And when one photon strikes this pixel, you can measure the signal which it creates. If you have two photons, for example, the second one hits the near pixel and creates also the signal. And also you simply summarize all these pixels and get the signal which is proportional to the original number of photons. Of course, there can be some problems if you have a very intense flashes of light. You may have a situation when, for example, two photons hit the same pixel. In this case, of course, you will lose the information about the initial energy, but this device was created specifically to detect low flash light, low flash supply, and it's used in many applications. It's not this device now hasn't fully replaced photomultiplier tubes because it's quite small. The maximum elements, you can see it here, It's about 6 by 6 millimeters. It's not big enough, and in order to create a significant area to detect light, we have to combine it and have a matrix of this silicon photovoltaic glass. And also, one advantage over photomultiplier tube is that in these silicon materials, you don't have to apply high electric field because the size is very small, several millimeters, and you apply up to 50 volts. If you compare to PNT, that's 1000 volts, and this allows you to get rid of high voltage systems, for example. Now, silicon photomultipliers found its application in scintillator detectors, of course, which are used in many applications, including fundamental physics, high energy physics. And apart from this fundamental applications, it's frequently used in such applications like LiDAR technologies, which are used for autonomous cars, for example. You have to detect light in order to measure distance between objects. In biophotonics, and in medical imaging, and this device is very important now. So, let's turn. Yeah, I think I got to turn to forward. So, sometimes it's very important to connect. As you can see, you have a scintillator and you have a photodetector. You have to connect them properly in order to get to receive all the light which produced during the ionization process, excitation process, when the ionizing particle passing through this scintillator. And for connecting these photomultiplier tubes and scintillators, usually you use materials which are called light guides, which can transfer light by total internal reflection, which is similar to the process which is happens in optical cables for internet connection. You process light, and here you can collect as more photons as possible. That is why you use these light guides. And the second thing, if you have a solid scintillator, you have to cover it with some kind of reflector. If you don't cover it with a reflector, you lose a lot of light. It will go isotropical, in all directions, never lose it. But you want all that light to go to this photomultiplier tube. That is why you show. That is why you cover your scintillator with reflection materials, which can be. There are a lot of ways to use different reflectors. Sometimes it's important to shift the wavelength of your light from, for example, a blue light to green light, and it's done by wavelength shifters. So I think I have covered all scintillator detectors and can move further because of time to talk about semiconductor materials which are used for detectors as well. And by covering these semiconductor materials, we can consider all really almost all conventional detectors, which are used in gamma spectroscopy, in neutron detection, and so on, and move to more practical things, how to detect, for example, gamma rays, how measure their energy, and how to detect, for example, neutrons, and understand the energy of neutron, and then calculate the number of them. And here, just the last type of detector I would like to show you, which is called the solid-state detectors, which utilize semiconductor materials, and both semiconductor materials have this crystalline structure. Most semiconductor have zinc blende or diamond structure. A picture of a crystalline structure you can see here. We have a lattice, and in lattices, in dots of this lattice, there are atoms which form this beautiful structure. You have distance between them, which is usually measured in angstroms, and there are typical materials which are used for semiconductor detectors, germanium and silicon. In some applications now, we use diamond materials, but the main property, the main advantage of diamond is on the fact that it can withstand high radiation doses compared to germanium or silicon. And here again, this band structure, we have a valence band, conduction band, and a band gap between them. And the main difference, you can hear three types of materials: conductor, semiconductor, and insulation. And the main difference between all three types of materials, that's actually the width of this band gap. For insulators, you have this width more than 5 electron volts. And why insulators don't conduct electricity? That's because this value is pretty high, and the process of conductivity starts happening when you have electrons from this valence band that can overcome this barrier and go to the conduction band. If you look at the conductors, you can see that there is no this gap between conduction and valence bands, and electrons can freely go to this territory, and that's you have electric current, for example, in metals, which are good conductors. And in the semiconductor case, you have the gap, which is approximately equal to 1 electron volt, and in some cases it can conduct current, and this property of semiconductors is used for radiation detectors. Electrons from this valence band can go to this conduction band in the case when you have pretty hot material, and the probability of electron go to this conduction band is described by this formula, and this formula just shows you that if you have more temperature, that probability is higher for electrons to go to this conduction band, and that is why in radiation detectors you have to keep this temperature as low as possible, because there are two processes which happen. Mostly in parallel, you have electrons that can go to this conduction band by means of thermal and the temperature, thermodynamic effects. And the second thing, they also can get some energy from the ionizing particle. And in this case, the electron also can get some energy and go to this conduction band. But it happens that the majority of materials, germanium and silicon, it's extremely difficult to achieve the purity and properties that can allow you to operate the detectors in this matter. You always have a high level of these parasitic effects, high current, which is mostly from the thermodynamic emission. You have to come up with some idea how to reduce this thing. Here comes the so-called PM junction, which is used in diodes in many semiconductor modern devices. And just remind you that in order to get this PM junction, you have to meet two materials, and these materials should contain P-type semiconductor, which is doped with elements like boron from the third column of the periodic element, and the second material should be from the fifth column of the periodic table, which is basically phosphor, for example, and you will get N-type semiconductor materials. If you meet them together, connect, of course, not just physically, but using specific techniques to increase the temperature and create this PM junction that creates the region which is called space charge region, and this created by the fact that negative areas start to drift towards the area where there is a lack of them due to the diffusion process. The same for P-type materials. And it will get this space charge region, which is called the depletion region. And if you apply significant, actually this region is free of charge carriers. And if apply an electric field in the inverse direction, it will create actually a small semiconductor detector, and this area serves as a semiconductor detector. And if we coming back to semiconductor detectors, they start operating like typical ionization chambers. You apply two electrodes, one anode, one cathode, and apply an electric field between them. And instead of electrons and ions, you will have electrons and holes, which can drift also under the influence of electric field to the opposite electrode. And then you, by the same technique as for ionization chambers, you collect this electric charge. And this allows you to get an amplitude, and then again, you can convert it in the energy of the initial particle. But what is the reason why we start doing the same thing with semiconductors to create quite complicated structures and create this PM junction? And the main reason is that the energy which is required to create electron into hole is much less compared to the energy which is required to create electron ion pair. That's the property of these semiconductor materials, and the energy of this, if you remember from the last lecture, the energy which is required to create electron ion pair, for example, in argon, is about 30 electron volts. Here in these semiconductor detectors, we have the energy which create this electron hole pair, which is approximately equal to 3 band gap energy. The band gap energy is about 1 eV, and for silicon and germanium, the energy per electron hole pair is about 3. Here is the number. What it gives you, that you have more charge carriers in your detector. When you have charge carriers, you will have more strong signal, and this more strong signal allows you to get the perfect energy resolution in order to get excellent ability to distinguish between gamma rays sources and give separate gamma ray lines. But it will be the topic of my next lecture, about why we use different detectors for gamma spectrometry and why semiconductor detectors are the best devices to use for distinguishing between different gamma isotopes. Thanks for your attention. If you have questions, I can answer them. Okay, I can answer them tomorrow.
Muy bien, como recomendación, por favor, mañana trataremos de pagar temprano, porque la próxima sesión mañana, el día viernes, las clases van a ser de 1 hora nada más, porque vamos a poner el examen en la partida en 4:30 de la tarde. Entonces, esta división es un poco como desanimante para los cursos profesores, ver que no hay mucha gente que estamos empezando con 5 o 6. Entonces, es muy agresivo por ejemplo, perdón, de estar más temprano mañana. Entonces, esa es la recomendación que quería hacer. No sé si tienen alguna consulta. Ustedes. Ok. Gracias por todo. Nos vemos mañana. Sí.
Sobre el examen de ser, ¿qué va a ser el formulario o hacer así con los que están en sus pacientes?
Estamos en este tiempo de que sea online, así que preguntas como se hacen por el mundo. La idea es que todas estén con sus ayudarás la presencia de la biblioteca. Porque el examen solo va a ser permitido fuera, los que están inscritos fuera, los recintos interiores, del exterior del país, fueron los que están inscritos para pasar clases presenciales que vigilar en el examen de transmisión en la biblioteca. ¿Está? Listo, gracias. Entonces,